Well, now the next two examples should be quite straightforward. I'd like to verify that these guys are a vector space, the first one being r square. Well, this should be pretty simple. R square, you should be convinced already because r square, this is your usual set of all the two-dimensional vectors. So this is the vectors in the plane in the usual sense. And these guys, well, we know how to add them. We can add two vectors. We already learned this stuff. It should not be hard to convince yourself that this set actually satisfies all these several properties. So let me actually just save us the time and not go through all each of them one by one again. R to the 3 power. So this is once again the set of all the usual three-dimensional vectors. So it's basically the set of all the vectors in three-dimensional. And this is once again also a vector space. Let me move on to the next one, r to the n. R to the n is basically just the set of vectors with n coordinate. If I were to write this guy out, it's gonna be v1, v2, and so on to vn, where my vi is a real number. So basically, this is the set of all vectors in n dimension. I don't really know how to draw the n dimension, but you get the idea. So we can add them, we can multiply them with scalars, no problem. So that's fine. This is also a vector space. Now the next one. The set of all infinite sequence is also a vector space. An infinite sequence is basically just a sequence of a real number. Let's say if I have 1, 2, 3, 4, 5, 6, 7, and so on. So this is one possible sequence. Let me actually write the parentheses around them. And let's say if I have 0, 1, 0, 1, 0, 1, 0, 1. So this is also another infinite sequence. Notice that how my sequence will actually keep going, just keep going forever. So this set, so my set will consist of a bunch of these. So my set will be the set of all infinite sequence. So whatever infinite sequence possible, my set will contain all of them. These guys is also a vector space, and that's because I can actually add two of them. I can add two infinite sequence together. If I add these two guys, that's gonna give me, well, just gonna write that down. That's gonna give me 1, 3, 3, 5, 5, 7, 7, and so on. So that means I can essentially add two infinite sequence together. I can also multiply an infinite sequence to a real number, no problem. So in a way, the set of all infinite sequence is also actually just a vector space. I can actually view this also as r to the infinity. Notice that how your vector in the usual sense, this vector has n coordinate. It just so happens that the set of all infinite sequence, I can view the infinite sequence as just a vector. But the number of coordinates that I have is just infinity. So I can view this guy, the set of all infinite sequence, as just r to the infinity. So there goes example 3.3. Let me now move on to the next one, example 3.4. I'd like to verify that the set of all matrices is not a vector space. Let's see. Usually, whenever something is not a vector space, the culprit is going to be one of the four things. So this is the four important one that I said before. Usually when something is not a vector space, one of the four properties is, it usually is violated. So let's look at my first one. If I actually add two matrices, well, it turns out if I have a 2 by 2 matrix, if I add a 2 by 2 matrix, I cannot add that to a 3 by 3 matrix. So in a way, it is not possible to add a 2 by 2 matrix with a 3 by 3 matrix. So that kind of means this is my vector. This is the set of all. If I look at the set of all matrix, this is one of the matrix. This is also one of the matrix. But when I add them, I don't really get anything. It doesn't have any meaning. So when I add two vectors, it turns out that it just falls outside my universe, which is the set of all metrics. So that violates the property 1 because it's not closed under addition. So this guy is basically not a vector space, and that's because it's possible that I add two vectors, in this case a matrix, and it's no longer a vector, which is, well, in this case a matrix. Let's look at my part B. The set of all 2 by 2 matrices is a vector space. Well, this should be pretty easy to see. If I now have just the 2 by 2 matrix, then I can add them, no problem. I can also multiply a 2 by 2 matrix with a number, and I also get another 2 by 2 matrix. I have the 0 vector, which is the matrix where the elements are all 0. I also have the negation of a matrix. I just changed the sign of all the entries here. And it also has the rest of the properties. So this guy, the set of all 2 by 2 matrices, is a vector space. The next one for my part C, the set of all 2 by 2 diagonal matrices is a vector space. A diagonal matrix are basically the matrix that only the entries in the diagonal can be non-zero. So these two guys can be anything, but the rest of them has to be 0. Now then, if I add a diagonal matrix with another diagonal matrix, then I'm gonna get, well, just another diagonal matrix, so it's actually closed under addition. If I multiply a number to a diagonal matrix, that's gonna give me a B and a C. So this is also yet another diagonal matrix. So it's actually closed under scalar multiplication. It has the 0 vector, it has the negative, I can change the sign of these two guys, and it has all these the remaining 8 properties. So this guy is also a vector space. And now my last one, the set of all 2 by 2 singular matrices is not a vector space. A singular matrix, by the way, this is the matrix where the determinant is 0. So, I need to show that this guy is not a vector space. So, let me just craft an example for you to see. Let's say if I have this matrix, which only has 1, 1 in the top left corner and the remaining entries are 0. This guy is a singular matrix because the determinant is 0. Now, I'm gonna add this matrix with another matrix that has a 1 in the bottom right corner and the remaining entries are 0. This is also a singular matrix because the determinant is 0. But now, notice how when I add these two matrices together, I actually get the identity matrix. I knew that the determinant of the identity matrix is 1, so the determinant of this guy is 1, so this is actually no longer singular. And it just so happens that when I add two singular matrices, I get something outside the universe. My universe now is the set of all 2 by 2 singular matrices. So when I add two singular matrices, I get something which is not a singular matrix. So it goes outside my universe. So that means my set of all 2 by 2 singular matrices is not a vector space, and that's because it's not closed under addition. When I add two vectors, I get something which is no longer in my universe, in my set of vectors here.